Okay, for this second part of 702, we're going to look at an AP practice problem. I apologize that this is a little bit blurry. Again, this was also the same one they used on that video I found on YouTube. They did a great job. And what we have here is we have a spring attached to a surface, and we put a mass on that, and then the student comes through and pulls down on the mass and releases it. And what they say is, I'm going to go ahead and scroll. On the dot below, draw and label the forces or components exerted on the block. So what we've got, they want basically the free body diagram. So I've got my block. I'm just going to write here. It's going to be easier. I'm going to have a spring force. So let's see, do they tell you the block is pulled downward and held in place? On the dot below, draw and label the forces exerted on the block. So before the block is released, we would have a gravitational force pulling, an applied force pulling down, and spring force pulling up. But really what we're going to be interested in here is part B. I'm kind of skipping over part A. It says the student, slide this up. The student releases the block. Consider the time during which the block is moving upward towards its equilibrium position, and the spring length is still longer than the distance it was pulled. So this is really where we want to start. I'm not going to do that free body diagram for part A. That was part of the easier work. A clear, coherent paragraph length response may also contain diagrams. Indicate why the total mechanical energy is increasing or decreasing or constant for each of the systems below. And what they do is they're defining the system three different ways: the block and the spring, the block, the spring, and the earth. So let's do that free body diagram now. And I'm going to go with, let's see if I can make that to level out. So here's my block. And I'm going to have, we're moving upwards. So we've got our motion. Let me grab my motion vector. I always do that in green. Our motion is this way, and that is with acceleration. So we're going to be accelerating up. So that means that my spring force, and I'm going to draw my spring up here, has to be greater than the force due to gravity. Here's Fg, and here's the ground. So that's my spring, that's the ground, and I should have maybe made my gravitational force a little smaller, but we see we have a net force going up. And in the first problem, they say, let's assume our system is just block. I'm going to bring a, let's see, let's go with purple. And I'm going to draw a dashed line around the block. Now, we said in the last video, if you have forces that are not contained within the system, they're external forces, and you're going to have an open system. And in fact, we do. So this is going to be an open system. If I look at these two forces, it should be a little more clear that this is larger than this one. I should have shortened up my gravity vector, but I have a net force. So my net force is going to be in this direction. Now, they want to know if how do they say this? The total mechanical energy is increasing or decreasing or constant for each of the systems listed below. One of the things that you don't know yet, and I'm going to go ahead and write this out. In the next video, we're going to talk about work is equal to the force that's exerted times the distance over which it's exerted. And what you need to know is that positive work, the force is in the same direction as in the motion. The force and motion are in the same direction. Same direction. If I have negative work, my force and my motion are in opposite direction. Opposite directions. In this case, my net force is in the same direction as the acceleration. So I am doing positive work on the block, that means that I'm going to add energy in and I'm going to increase. And I'm going to do ME for mechanical energy. Notice we're specifying mechanical energy, not thermal energy, not nuclear energy, not electrical energy. So this is all mechanical energy. In the next system, they want us to do the block and the spring. So I'm going to redraw my diagram. I'm going to make, I know I always tell you don't change the length of the gravity vector, but I want it to be a little more apparent. So here's my spring. Here's the ground. Here's my block. And I'm going to do force of the spring, force of gravity. And this time they want the block and the spring to be the system. So in purple, I'm going to use my purple to outline. And look what happened. Now the spring force is internal, the gravity force is external. My motion hasn't changed. I still have acceleration going in the upward system. This is going to be conserved because it's internal to the system. This one is not. Gravity is now doing work against the motion because this force, so this is now an external force. And this is in the opposite direction of motion. I am now doing negative work. So I'm going to decrease the energy of the system. You know what? I'm going to write this up here. I'm going to decrease the energy of the system. Now they want to know what happens if I do the block, the spring, and the earth. The block, spring, and the earth. So let's draw another one. The ground. Now I'm going to bring my dotted lines to define my system all the way around. And look at what has happened. I have internal forces only. Now, because I changed my system to include the spring, the ground, and my block, that means that I have everything is internal, and I'm not going to have any external forces. So I now have, the other thing I didn't say was this was an open system. I now have a closed system. And all of the energy within this system, so I'll go to black. So here my energy is going to be conserved within the system. And so I have constant. So for the first example, I was increasing the energy of the system. For the second one, I was decreasing the energy of the system. And for the third one, my energy is conserved within the system. Let's add that within the system. All because I changed the way I define my system. So I cannot emphasize enough how important system definition is at the start of your problem. I know when we worked with force and kinematics, I always said you have to define your coordinate system. Now we're going a step further and you have to define the entire system. Okay, that wraps up our introduction and definition of open and closed systems. I should say there's one more type of system. It's called an isolated system. There really isn't any such thing as a perfectly closed system. It just doesn't happen where we're able to keep the energy perfectly conserved unless you have an isolated system. And an example of an isolated system is our universe. Scientists, as best as they can determine, there is zero loss of energy or matter within our entire universe. And so the universe actually acts as an isolated, perfectly isolated system. All right, that's all for this one. We're going to start to talk about work and the specifics of it in the next video. Thanks for watching.